Hi everyone. Isaac Newton was a curious child. Curious as in always questioning for a knowledge. According to one story, he would become so engaged in reading that he used to forget his lunch, dinner, and his pet cat grew fat by eating his untouched meals. Or consider his first exploration of optics. Ever met a kid so curious he had risked his own sight for a glimpse of the truth? He stuck a bodkin, a long shaving needle with a blunt point, into his eye socket, between eye and bone, and recorded seeing colored circles and other visual phenomena. Today we rarely remember Newton as the self-torturer owner of a fat cat. Instead we remember him as a guy who got hit by an apple. Sir Isaac Newton himself said that glimpse of a falling apple made him think about the power of gravity. No matter how high we rise, rooftops, treetops, mountaintops, gravity doesn't diminish. The matter of Earth seems to attract the matter of objects no matter how far they are. The curious young man explored further. What if gravity reaches beyond the mountaintops? What if its pull extends outward further than we have guessed? What if it goes all the way to the moon? Well, in the spring of 1666, the madman was 23 years old, relaxing in the shade of his mother's garden. He watched an apple fall, and then by some inspired stroke, he imagined a second falling apple, this one as distant as the moon. He knew the distance, roughly. If Earth's surface sits 1 unit from its center, then the moon is 60 units away. At such a tremendous distance between them, how might gravity act? Gravity decays at a greater distances. The farther you go, the weaker will be its force. I am referring to the Newton's famous inverse square law. At twice the distance, there is 1/4 of the gravity. At triple the distance, 1/9 of the gravity. At 10 times the distance, just 1/100th part of the gravity. Our brave spacefaring apple, 60 times farther away from the Earth's core, would experience just 1/3600th part of the gravity. Drop an apple near the surface of the Earth, it falls 4.9 meters in the first second. That's about the height of the second-story building. Drop our apple from the moon height, and the first second it descends just over 1.36 millimeters. That's the thickness of a nice credit card. Back then, the explanation of a moon orbit was an open mystery. René Descartes' vortex theory, that all heavenly objects are swept along in their paths by swirling bands of the particles, like bath toys circling a drain. This was the favorite theory at the time, but this was a time of change. During plague time, Newton formulated his laws of motion, unlocked the optical secrets of the prism, managed to keep his eyes free of household objects, and discovered calculus. Newton's soul brother Galileo knew that horizontal motion doesn't affect the vertical motion. Drop an apple, launch an identical apple sideways, and they will hit the ground at the same time. Sure, their horizontal trajectories are different, but their vertical motion obeys the same law, gravity. Now take your apple to the moon height and throw the apple really hard. It will travel a little distance before falling to the earth. It may reach point A or B. Throw the apple really hard and its horizontal motion now leads it away from the planet. Perhaps it travels all the way to the sea. Throw the apple very hard and it flies away from the earth so fast that each moment's falling merely restores the apple to its original height. The apple can thereby fall forever. An orbit is just a perpetual fall. So consider a virtually infinitesimal moment, a single second of travel. Over such a brief interval, the curved arc can be considered as a straight line. Here 1.36 mm is the distance that an apple would fall if it wouldn't have horizontal velocity. Now what? Newton's next move is a useful geometric argument. We have created a little right angle triangle. We want to know its hypotenuse, the longest side. So we make a larger triangle that shares the same proportion. Because the triangles are the same shape, their sides relate by the same ratio. Solving this equation gives the following solution. Our apple descends at the gentle rate of 1.36 mm per second, about 10% the speed of a snail. And yet, to keep the fruit in the orbit, we throw it sideways at a speed of roughly 1 km per second, about the triple the speed of sound. This really struck me. The moon falling like a thrown apple? Really, Sir Isaac? Can you confirm this? We'll consider the time our moon apple needs to circle the Earth. At such an enormous distance, it will have to traverse a path of 2.4 million kilometers in the circumference. Moving just over 1 kilometer per second, how long will this take? Look at that. Our computation matches to within less than 0.3% error. This number gives stunning confirmation of Newton's theory. The moon really is falling like a giant red apple. Sir Isaac Newton's theory identified a single universal force to govern the earthly and heavenly realms, birthing a modern vision of reality. The mechanical universe, a clockwork cosmos that obeys a definite and unbreakable laws. Thanks for watching.